Hey guys, this is part 3 of the June 2017 AQA Further Maths Paper 2. So I've decided this is a 4-video operation. We've got some big questions coming up, so I want to give each of them the time that they deserve. So in this video we're going to do questions 17, 18, 19 and 20, and we'll finish off in part 4. So, for question 17, we've got the graph of y equals x cubed minus 6x plus 7. So here's our lovely graph. Now we want to use differentiation to find the coordinates of the stationary point, which is a minimum. So that is this point here. That's our minimum. So that tells us then that the x-coordinate is going to be positive and the y-coordinate is going to be negative. So we need to differentiate the function. So our function is x cubed minus 6x squared plus 7. So dy by dx is going to be 3x squared minus 12x. Now, we know at a stationary point, the gradient is equal to 0. So remember, the reason we differentiate is to get the gradient function. So we now set this equal to 0. So we got 3x squared minus 12x is equal to 0. We've got a common factor of 3, divide that away. X squared minus 4x is equal to 0, and then factorize this, we get x times x minus 4 is equal to 0. So we've got two possible solutions for x. Either x is 0, but that is for this stationary point up here. We don't want that one. We want x equals 4. So there's half of what we're after. We know the x-coordinate is 4. So to find the y-coordinate, we now substitute that into the function. So we're going to get y equals 4 cubed minus 6 times 4 squared, which is 16. So minus 6 times 16 plus 7, and that will give us, well, 4 cubed is 64, plus 7 is 71, 6 times 16 is 96, so we've got 71 minus 96, so we've got minus 25. Of course, this being a calculator paper, use your calculator for that. So our y-coordinate is minus 25. Good times. Okay, and then we're told the 3 roots of the function are the x-coordinates, where the graph cuts the x-axis. So that's what roots are. Nice of them to remind us. So we want to show that x equals minus 1 is a root of our function. So to do that, we just substitute it in and show that we get 0. So we're going to get minus 1 cubed minus 6 lots of minus 1 squared plus 7. Now minus 1 cubed is minus 1. Minus 1 squared is 1. Times that by minus 6 gives us minus 6. So we've got minus 1 minus 6 plus 7, and that does indeed equals 0, so x equals minus 1 is a root. Okay, then part C, here's one of those big questions I was talking about. So, using what we've just done above, we want to work out the other two roots of our function. So, first of all, we need to remember the factor theorem. So, if x equals minus 1 is a root, that means that x plus 1 is a factor of our function. So that's the factor theorem. So when I'm on about factors, I mean algebraic factors. So, for example, if we had the function x plus 1 times x plus 2, they are both separate factors of a quadratic. Here we've got a cubic function, so we can have as many as 3 different factors. So x plus 1 is one of them. So we know that our whole function is x plus 1, which is a linear factor, times some quadratic factor. So we know that we've got a single x cubed in our function. So our quadratic function is going to have a single x squared like that, plus bx plus c, like that. So we need to first of all find the values of b and c. Now, if we compare our linear and quadratic factors there to the actual function, in the actual function we have a plus 7 at the end. So what's going to produce that for us is the 1 here times this c at the end. So that tells us that c is equal to 7. So we can now say our linear factor is x plus 1 and our quadratic factor is x squared plus bx plus 7. So now we need to find the value of b. So given that b is attached to our x term, let's work out from the expansion what x terms we would get, then compare that to the x term in the function, and we will be able to work out the value of b. So in this expansion we are going to get x terms when we do 1 times bx, so that's going to give us bx, and also when we do 7 times x, so we're going to get bx plus 7x. Now we know that has to be exactly the same as the x term in the original function. Now there is no x term here, so there are 0 x's. So we, in other words, then need bx plus 7x to equal 0. If we take the 7x away, bx is equal to minus 7x, so b equals minus 7. So, in factorised form at the moment, our cubic is x plus 1 times x squared minus 7x plus 7. Okay, so we now have our cubic function in terms of a linear factor and a quadratic factor. Now we know the solution that the linear factor gives us. We now need to solve the quadratic factor equal to 0. So, it doesn't get any nicer even though we've done all of that previously. We are now solving x squared minus 7x plus 7 is equal to 0. So, it's quadratic formula time. Yay. So, A is 1, B is minus 7, C is positive 7. So, the quadratic formula is given to you at the start. Okay, so we're going to get x is equal to minus 7, so positive 7, plus or minus the square root of minus 7 squared is positive 49, minus 4 times 1 times 7, so that's going to give us minus 28, that's all over 2 times 1, so 2, so we've got 7 plus or minus the square root of 21 all over 2, so we've now got our two solutions. We've got 7 plus root 21 all over 2, which is equal to something. Do that in a second. And 7 minus root 21 all over 2. So I think they wanted this to 2 decimal places. Yes, they did. So it's calculator time. Okay, so finally we get 5.79 and 1.21. Jesus Christ, can you see what I said? I'm breaking this into 4 videos. Lovely. Question 18, the slightly nicer. So here we got a rectangular height of x, length of 2x, and a diagonal of 4y. We are asked for an expression in terms of y for the area of this rectangle. So, first of all, area in terms of x. The area at the moment, or not even at the moment, the area of this rectangle in terms of x is 2x squared. Now we need to find an expression for x in terms of y. So, Pythagoras, we've got a right angle triangle going on here. We know if we call this side A, this side B, this side C, we know x squared plus 2x all squared, so plus 4x squared is equal to 4y all squared. So 4y all squared is, need an equal sign first, so that's equal to 16y squared. So that's 5x squared equal to 16y squared. If we divide by 5, we get x squared is equal to 16y squared over 5. So we don't need to find out what x is because we've got our area, which is 2x squared. We don't know what x squared is. It's 16y squared over 5. So we just substitute that in now. Our area is 2 times 16y squared over 5. So 32y squared over 5. Much nicer than the last question. Okay, question 19, we got some trick fun. So we're told that alpha is an acute angle less than 90 degrees. That is important to remember, first of all. So we got our graph of sine of x there. So as I said, alpha is an acute angle less than 90 degrees. Sine of alpha is equal to k, where k is a constant. We want to write the answers to each of the following in terms of k without knowing the trigonometric functions. So, first of all, what I'm going to do is play with the graph a little bit. So, k is just a constant. So, let's go down a bit. Let's say this is our horizontal line, roughly. Y is equal to k. So, when we go along the bottom and we plug in our value sine of alpha, we hit this point on our curve, or actually this point too. So this is going to help us solve part A. So part A asks us for sine of 180 minus alpha. So let's go back to our graph here. So remember, the trig graphs are symmetrical down the middle. That's going to help us. So we're symmetrical down there. Now, alpha is alpha degrees in from 0. So 180 minus alpha is alpha degrees back from 180. So sine of 180 minus alpha is actually just going to have exactly the same solution as sine of alpha, which is k. So k is our answer to part A. Then we're asked about sine of 360 minus alpha. So what's going to happen there then? Well, 360 minus alpha is just going to take us down there. So we're going to hit the same y value on our curve, except it's going to be negative. So this is going to be y equals minus k. It would be the same as well when I asked a bit of bonus information. It would be the same here for sine of 180 plus alpha. That would also be minus k. So our answer to part B is minus k. Okay, and then for part C we want cos of alpha. So for this we need to use one of our trigonometric identities, namely sine squared plus cos squared is equal to 1. Now we know that sine of alpha is k, so sine squared of alpha is k squared. So we've got k squared plus cos squared alpha equals 1. Take away k squared, cos squared alpha is 1 minus k squared, and then square root cos of alpha is the square root of 1 minus k squared. Good times. One more question. Okay, question 20. So this is the last question for part 3. I'm glad I made the decision to break this up. after this, I'm going to go have a lie down. This has been very intense. So, part A, we've got these circles and some lines and stuff. If you want to read what's going on, there you go. I think it's pretty self-explanatory though. So, we've got two circles. First of all, we are asked to give a reason why angle BEA is 90 degrees. So, angle BEA is this top here. Now this guy is a right angle because the line BA is a diameter. And then we've got two chords coming off of the diameter like that. When we got that situation, they always meet at right angles. So the reason BEA is a right angle is because BA is a diameter. Okay, this is about to get a lot funner in part B. And then for part B, we want to prove that angle DCE equals 2x. So, back to the diagram for this. So, we've already said in part A, this angle is a right angle. That means then, the third angle inside this triangle, ABE, is 90 minus x. So this angle here is 90 minus x, which then means that this angle here is 90 plus x. So 90 plus x and 90 minus x adds together to 180 as we need it to. So if we then zoom out, in the left hand circle we've got a cyclic quadrilateral going on. So that guy is a cyclic quadrilateral. In cyclic quadrilaterals, opposite angles add together to 180. So if this purple angle is 90 plus x, and this bottom left angle is 90 minus x. Now we're in an isosceles triangle, so this bottom angle on the right is also 90 minus x. So at the moment, the inside of this triangle, our angles add up to 90 minus x, add 90 minus x, which is 180 minus 2x. If we call this angle the one that we want, let's call him angle y. Y is then 180 minus 180 minus 2x, which gives us 180 minus 180 is nothing, minus 2x tells us that y is 2x as we need him to be. Okay guys, that's it for part 3. Can't believe I'm saying that, but we will finish off in part 4.